The title of my talk is Machine Learning and the Brain. As mentioned now, I'm Associate Professor at Stellenbosch University in South Africa. I'm the current head, well, for the next 6 months still, the current head of the Biomedical Engineering Research Group, and that's a research group within the Department of Mechanical and Mechatronic Engineering. And it is only a sort of postgraduate research group, so master's, PhD students, and postdocs. And within this group, I sort of focus on neuroscience, and the last couple of years also bringing in a bit of machine learning in helping to understand the brain. So, I mean, the brain is just so fascinating and interesting, and still clouded in mystery. I mean, we've got this 1.4 kilogram jelly-like organ behind our eyes, between the ears, and it's responsible for our every thought, emotion, experience, every action, and yet we still don't really know exactly how all of this happens. And so I decided that, given my background and skills as an engineer, let's try and see if we can use those skills and try and better understand the brain. So I just quickly want to mention why machine learning also. So most of the work we do is with EEG. So it's measuring the electrical activity in the brain. That's been the first human EEG was done in 1924. So, I mean, it's 100 years ago already. But interestingly enough, a lot of the signal processing and analysis is sort of also comes from the 1924. It's really basic and simplistic. So there's sort of two main ways of analyzing EEG data. And that's what they call ERPs. It's event-related potentials. So that's where you stick someone in front of a computer with the EEG on their head, and you repeat a task many times. So there's a specific stimulus you're interested in. You repeat it many times, and then you average all the EEG data to sort of get rid of noise, and you look at the time series trends. So that's the one way. And the other is power spectral density analysis. So basically, you break the EEG signal up into different frequency bands. So you've all probably heard about the different frequency bands people talk about. That's delta, theta, alpha, beta, and gamma. And then you just look at the power in each frequency band, and people say is there an increase or decrease in power given a certain task or cognitive load or whatever. And most EEG studies have sort of just followed that trend using those tools. I have to add in let's say the last decades, there has been some new sort of techniques used, and they look at synchrony between different brain areas, and there's what they call entropy, EEG entropy. But there's still not a lot of machine learning in trying to analyze EEG data. So it's sort of there's this niche that one can explore. And so I like both machine learning and the brain, and decided, okay, let's combine the two and see what one can figure out. Okay, there we go. So, okay, quickly back to where I'm from. So yes, I'm not sure if you can see my cursor, but top you can. Okay, great. So South Africa, probably it's in the name, it's south of Africa, over there. And then in South Africa, you go to the southwestern tip over there, you get Cape Town, and I'll show you in the top right corner. Beautiful Cape Town. And then from Cape Town, it's a 45-minute drive inland to Stellenbosch. And Stellenbosch is sort of the winelands of South Africa. It's sort of our Napa Valley. There's a lot of vineyards, and then we have the university in Stellenbosch. So Stellenbosch is famous for two things: wine and students. And beautiful place, but I've been at Stellenbosch University now for 18, almost 19 years, including as a student. So it's time for something new, and that's why I'm heading to the US in a while. Okay, so I'm going to jump straight into the rest of the talk, and basically what I'm talking about today is 4 sort of recent studies we did. So all of the work I'm talking about will be work I've done in collaboration with students. So as you know, the students do most of the work. I sort of delegate, and I have the crazy ideas and I get them to do most of the work. So I'll be talking about some of the work we've done literally the last 2-3 years. 4 quick studies in how we use machine learning to try and understand the brain, and answering some of these fundamental questions of how does the brain encode information, and then we'll also get to some of the more philosophical questions. So first up, so decoding the brain. So a study we did this was sort of one of the first ones we wanted to look at. So you can see here on the guy's head is the EEG. So a lot of these electrodes. This is a 128 channel EEG system. And I'll play the video quickly. Basically, all we did here was we showed the participants basic shapes on the computer screen. So you'll see a circle there, and now there's a square flickering. And then we record the EEG. So you'll see all of these are the channels, and you see these squiggly lines. That's the EEG signals, the electrical activity we record. So basically for this sort of first exploratory project, and there you see a cross, we had 10 participants. I can hear myself talking there on the video. So we had 10 participants, and we showed them 4 basic shapes. So we had the circle, square, cross, and a triangle. And we just sort of showed, I think it was in 500 millisecond flickers for, I think it was something like 10 seconds or 7 seconds. And we showed each shape, I have to remember, I think 18 times, 20 times, something like that, while recording the EEG. And then the whole idea was just to see if afterwards, if you can classify what the person was looking at based just on the EEG signals. So in a way that it gives you information on, does the brain encode, how does the brain encode what it saw? And I mean, we did it across 10 participants, so you can start asking questions like, was it similar between the 10 participants? So if you train a machine learning algorithm to classify based on the EEG signals, can it generalize between participants? And you can also start playing around with looking at different sets of the EEG electrodes and seeing if you only use a certain set of electrodes, what does that do to your accuracy in classifying what the person looked at? And so but basically what you're looking for is are there neural correlates in the brain that you can pick up with the EEG that corresponds to the simple shapes they look at? And so in this specific case, what we did was, so like I said, we had 10 participants, 4 shapes, and they looked at each shape about 20 times. What we then did was, well, the student working on this project, he wanted to be all fancy. So he sort of developed this maybe a bit over the top machine learning sort of whole setup here. So he took each channel, and for each of the 128 EEG channels, he took the frequency band. So you'll see here there's the theta, alpha, and beta. So only sort of the middle 3 frequency bands. The lowest one, delta, is 0 to 4 hertz. Then you get theta, that's about 4 to 8 hertz. Alpha is 8 to 12, and then beta 12 to 20, and then you get gamma. So we only looked at these middle ones, theta, alpha, beta. And most of your waking cognitive functioning will be in that, maybe a bit of gamma. So took those three and looked at, you'll see also a certain time slice, and looked at the power in each frequency band. And we turned that into red, green, and blue, so RGB, which we then use to make pictures of the brain. So over here, you'll see the EEG, the image we created. That's every sort of pixel here corresponds to a place on the head, and we make a sort of each pixel has an RGB value created from the EEG. And so he wanted to create images because I don't know how familiar you guys are with neural networks and machine learning, but convolutional neural networks are especially good at working with images. And so we created this sort of EEG image, feed it into our convolutional network, and then we try and predict what the person was looking at. So maybe again, also, if you're not too familiar, what you usually do is if you have, you take all your data you recorded, and then you split it up into a training set and a testing set. So you'll typically take, let's say, 75% of the data, and you train your machine learning algorithms on that 75%. And you leave a 25% of the data completely out for testing. So you don't want to train your model on the data you're going to test with. Otherwise, you're going to get skewed results. So typically take 25% of the data out, leave it one side, build and train your algorithms on sort of 75% of the data, and then afterwards you test. And in this case, the student, I mean, he spent a lot of time working on this fancy convolutional network model. There's a lot of parameters you choose and tweak, and there's a lot of, it's an iterative process to sort of tweak your model before you get to the testing. And as a good supervisor probably should, I told them, okay, but listen, also just compare this fancy model of yours with other sort of more basic models. And then quickly, here's some of the results. So you'll see a lot of the other machine learning models. There's support vector machines, KNNs, that's K nearest neighbors. Here's the CNN, and the GAN CNN is just a generative adversarial network CNN, meaning he sort of created artificial extra data using GANs, and then run the CNN again. So with the CNN, we got 73% accuracy. Hopefully you'll figure out that chance would have been 25% given the 4 shapes. So 73% it's well above chance. So there's the machine learning algorithm. There is something in it. It can with relative accuracy predict what shape the person is looking at. But the interesting one for us afterwards was the 93% accuracy of a KNN. And a KNN is really one of your most basic machine learning algorithms. It's basically, it just clusters. You say how many clusters it should form, and it forms clusters. And and this was done just on the raw data. So we didn't make the image, didn't go through all of that, just on raw data, make clusters, and we got 93% accuracy with a KNN. Between 10 participants. So it leads to one to think that maybe there's some generalizability between participants in how the brain encodes the shapes. And maybe for something like these basic shapes, there's sort of an easier answer than trying to go into very, hectic deep learning algorithms like the CNN.
May I ask a question?
Yes, you're welcome.
So did you trained on all of the 10 subjects data, and then you looked, so you divided the data you said into 2 sets, the sort of training set and
Yeah,
the test
yes,
set,
yes.
with just the 4 shapes shown? Is that correct?
Yes, that's correct.
Okay. And how many layers were there to the convolutional neural network?
Honestly, I can't tell you now. I can check afterwards if I open the paper. I just can't remember off the top of my head now.
Okay.
But I can check for you afterwards. I can send you an email if you're really interested. Yes, like I said, the students they're more aware of the more technical parts of all of this. I'm just sort of at top and delegating. So. But I can quickly check after this.
Okay.
And I can let you know.
I'm just wondering how sensitive it is to, if you used 3 layers or 8 layers or 12 layers, would the results vary a lot?
Yeah. I don't think it varied a lot, because I remember the student, he was playing around with it a lot. Tweaking, so trying different layers, trying different dropout numbers, all of that. And it was always around about 70, low 70%. We were really trying to push it up, but it doesn't matter what he tried, we were always around the 70, 73%. So I don't think it was too sensitive to the number of layers.
Oh, one other question, and that is, were the 4 shapes always the same size, or was there any effort to see whether it could do recognition in a size invariant way?
No, it was always the same size.
Okay, all right, thanks.
But I'll get to some of your sort of where your mind's going into the next one, and you'll see.
Okay.
Okay. Just quickly, also what we did after collecting the data, so we tried to see what's the effect on accuracy if we don't look at all 128 channels. So this is basically a visual task. So just sort of looking at shapes. And visual processing happens at the back of the brain, occipital lobes. So we said, okay, let's only use 28 channels on the back of the head and see the accuracy we get when we only use those channels to predict. And doing that with the CNN, the accuracy went down to 53%. Now, the interesting part is we then said, okay, what about if we look at only frontal lobes? So we only used, a bit more, but 56 channels, EEG channels on the frontal lobes. And then we had an accuracy of about 72%. So close to whole brain, all 128 channels. So in a way, saying that a lot of what we see in predicting, and so sort of how the brain encodes, or in this instance, is using the frontal lobe electrodes. So this got us sort of thinking, and we went into a second sort of iteration of this general idea, and we said, okay, we learned a couple of lessons. There's a couple of things we can look at now. So forget about the shapes. Let's take different sort of concepts, different classes. So instead of just showing a shape, we said, okay, let's do sort of sets of different classes of concepts. So we had numbers, and in each class we had 2 exemplars. So in numbers we had the number 2 and 7. For colors we had red and purple, and then objects we had a soccer ball and a pen. So in this case we had 6 different concepts. The problem we have with a lot of these types of things, so there's a lot of work on this called semantic categorization, and seeing how the brain encodes different categories of things. But a big problem with a lot of this is there can be a lot of confounding variables affecting the EEG. So for instance, if you just show images, you're not sure if you evoke or if you're measuring the actual sort of concept the guy has, or is it just sort of the raw the complexity of the image that you're picking up in the EEGs. Or if you're using words, let's say soccer ball over here versus pen, are you actually getting to the actual concept, or is what you're seeing in the EEG and what you're predicting, is that only based on lexical frequency. So just because there's more letters in soccer ball than pen, are you picking up the more letters, or are you actually picking up concept of soccer ball versus concept of pen? And so to try and get around that sort of problem in a lot of these, we decided, okay, let's present each of these exemplars in 3 different ways. So to sort of try and make sure that what we are forcing our machine learning algorithm to recognize is not the number of letters or the image complexity, but rather the actual concept. So for 2, we showed a 2, like the letter 2. We showed the word 2, and we also used Roman numerals. And then similar for let's say for the colors, we used an image of just red. We wrote out the word red, and we would say, what is the color of blood? And then for objects, the image of a pen, the word pen, and something you write with. So 3 different ways to get the same concept in a person's mind, to make sure we train the machine learning algorithm on the concepts and not just sort of the raw image or number of letters, something like that. And then we also, in a lot of these semantic categorization things, there's a lot of assumptions people make. So the first assumption is that, firstly, there is neural correlates for different categories. So that there is something you can actually pick up. So that's sort of an assumption you make before the time. Another assumption is that these neural correlates persist over time. And then a third one is that you can actually generalize this across people. And we said, okay, let's do this, but we make none of those assumptions, and we just see what we get. And one should also always keep in mind that, of course, the brain is very complex and non-linear. So it makes sense to rather use something like machine learning that's a non-linear tool to analyze the data. Okay, so we did this, and we got interesting results. So unfortunately, this was a rather small study. So this is very recent, sort of like a pilot study. So there's a lot more we want to do, but we only used 4 participants. We showed each of these exemplars, let's say like the number 2, we showed to each participant 150 times. So we had 5 sort of sessions of 30 each. So we showed, let's say, the image of a pen 30 times, well, 150 times, the word pen 150 times, and something you write with 150 times for all 4. So it took quite a lot of time. But in the end, we had about 10,000 data sets per, well, not per, but in all, per participant. No, not per. Over all 4 participants, we had 10,000 data points. And then we again just went to the convolutional neural networks, not using that image, just putting in the raw data, the raw EEG values, and seeing how we can predict. So, Alan, I think maybe what you also referred to was you asked whether we, in the shapes, whether we just trained it on everyone, on all the participants together. So we realized there that we sort of made an assumption that you can generalize. So what we did in this one also is we said, okay, let's first look per participant. If we just go per participant, so we train, so we just take one participant, we train on his data and test on only his data. So again, you split the data in the training and testing phase. And if we do that, between all 6 of these, numbers, colors, and objects, we get 99% accuracy on single participants. I mean, so that sort of answers the first assumption. Are there neural correlates for these categories? Sort of, you can safely say yes. There is something that the machine learning picks up in just the EEG data. So it can pretty accurately predict what the person is sort of thinking about. When you include all 4 participants, so take all 4 of them, you train on a subset of all 4, and you test on it. Then it sort of drops to 97%. But so there's a slight drop. But again, you trained your model on data from all 4 participants. So then we said, okay, what if we train the model only on 3 of the participants? Can we predict the 4th guy? So that will say if you can really generalize to unseen data. Does everyone sort of encodes information the same? So if that's yes, you should be able to train on 3 people and predict on the 4th guy. If it's sort of if we all brains encode similarly. And there we see that not really. So in this case, chance would have been around 16%. Our accuracy dropped to 26% if we trained on only 3 and then try to predict on the 4th guy. So that's sort of interesting. But like I said, only 4 participants. So plans for the future is to of course, increase the population size. And then something else we also want to do is that would be interesting is to see if, okay, what if you test on a participant, so you record a participant's data today, then maybe tomorrow, and then give it a gap of maybe 2 or 3 months and do it again. And see if you train on today's data, can you predict 2 or 3 months in advance? Or afterwards, can you predict on that data? And that will sort of answer the question of, does these neural correlates persist over time? Are they sort of fixed, or are they not fixed? And a lot of this also has to do with there's the question in the field of how the brain encodes the information. So is it mostly encoded? Is the encoding localized? So let's say, do you have a certain part of the brain that recognizes pen and soccer ball? Is it localized, or is it more a distributed network of recognizing? And again, one can play around with the different electrodes and see if there's an effect. So we haven't done that yet, but that's part of future studies that one can look at, trying to answer that question of whether it's distributed or localized. Just quickly check the time. Okay, so quickly jumping into some of the more the fun, interesting questions, the philosophical side of life and neuroscience. So neural correlates of decision making, that's just a fancy word for saying free will. Do you have free will? So one of the first studies on sort of addressing this question was done in 1983. I mean, that's almost 40 years ago, by Benjamin Libet. And basically what he did was he had these participants sit in front of a computer screen like this, and he had this clock on the screen, and he basically told him, just watch the dots. This little dot makes a revolution in just under 3 seconds. Watch the dots. And so they had the EEG on, and also something on their wrist, that EMG that measured the moment you move your wrist. And he told him to just move your wrist whenever you feel the urge to, whenever you want to. It's a completely free choice. When you want to move your wrist, move your wrist. But he asked him to just notice where this dot is on the screen. Did this with a couple of people. The processing of data. So this is typically what an ERP looks like, an event-related potential. So we have our events over here. That's the action of wrist movement. If you do this on the same person, let's say 50 times, you can get the average of all the data. So this is just for one electrode. Typically CZ, it's the one here in the middle, top of your head. Average all the data, and then if you average all the data, you sort of get rid of most of the noise, the random noise, and you can see the trends in the data. So the interesting thing they found was, that, again, this is about 40 years ago. Here at 0 milliseconds is action. That's when the person moved his wrist. About 200 milliseconds before action, that's when the person became aware of his intention to move his wrist. But 350 milliseconds before that even, there was a rise in an EEG signal. So this is called the readiness potential. And so basically what they said is 350 milliseconds before you are consciously aware of your intention to move, you can already see in the brain signals that you will move. So it precedes your conscious intention to move. Your brain is saying you're going to move now. So do you still have free will in this sense? I mean, a lot of this also depends on your definition of free will and your stance on free will. But for most, I want to say lay people, you have sort of the feeling that consciousness comes first. I first make a conscious decision that then sort of influences the brain to make the movement. But then Libet said no. Well, Libet wasn't really a fan of his own results. He tried to still save free will with the free won't get into that. But basically, okay, afterwards there was a lot of criticism on exactly his exact methodology. So for instance, a lot of people said we're working on millisecond scale here. That's it's really close to each other, and it's very difficult to exactly pinpoint when you become consciously aware of your decision. So when we're working in milliseconds and you have this sort of really difficult thing to pinpoint, we can't really take it seriously. That was the one big criticism. And the other one was, of course, that an urge to move isn't really a free will decision. There's no real world consequences. And I mean, this is a really fun one to try and take on with machine learning. So we said, okay, let's do this, something similar, but we can use machine learning. So we made one or two changes. So firstly, we did sort of exactly the same thing with the Libet clock, but we just instructed our participants to not just move a hand, but to either choose left or right. So they had their fingers on the keyboards and they had to press either left or right. Again, when they feel they want to, so completely free. And this sort of also introduces a choice, either left or right. So choose left or right whenever you feel like it. Just notice where the dot is when you make your decision. And so this just shows our ERPs. Again, you'll see it's on CZ, so that's the electrode over here. And it looks similar to Libet's finding here. So we also get the vertical line over here, that's when movement occurs. And we have about 400 milliseconds before movement, we have the rise of the readiness potential. Okay, so we had confidence that we get something similar. Then, of course, the fun starts. Now we can say, okay, what if we use machine learning and go even earlier? If we use, let's say, data from a second and a half to a second, we use like that 500 milliseconds, can we use that data to predict left or right movement? And playing around with that, okay, we'll get to that now. I thought I had another slide after this one, but basically, yes, we can. But I have to say now that at the moment, so we did this, we got 99% accuracy in left, right. And again, we had many participants. We had 21 participants for this with 128 trials per participant. So a lot of data. And we get 99% accuracy in predicting left or right movement. I'm showing here, let's say about a second before actual movement. That's 500 million. Well, in our one, we had our awareness of the attention to move 110 milliseconds before movement. So you can say almost 900 milliseconds, almost a second before movement, we get 99% accuracy in predicting. But what I'm not showing is we played around with it a bit more, and we can actually predict movement. Again, with something like 98% accuracy, almost 3.5 seconds before actual movement. So this is just where I need to, this warning, this is pretty recent findings. So that's why I don't even have the picture for 3.5 seconds before. But we are a bit skeptical. So we just need to check the students' machine learning algorithm and make sure there wasn't a mistake. But if everything pans out nicely, we're hoping for a really good publication out of this. So, but I don't want to jump the gun and be too excited. We need someone that really knows this stuff to just check the machine.
May I ask a question again?
Yes, go for it.
So is this based on all the channels or a subset of the channels?
So the machine learning part was based on all the channels. Again, we used all 128 channels for this. Yeah.
So, there's work going way back in non-human primates, like Shadlin and Newsom, 1975, and Jeff Shaw and his colleagues, where they were recording from parietal cortex or areas in the frontal lobe, where they actually, the monkey's got a task when looking at, for example, a noisy motion field, and has to say, is the movement to the left or to the right? And you can actually see this sort of buildup of neural activity prior to the decision. And sometimes, of course, if it's a really noisy field, they make mistakes quite a lot. But you can still see either the buildup or the build down in particular neurons. You know that work?
Yeah. I've heard something similar. Exactly.
Okay, so I mean, that kind of thing goes back at least, around 25 years, so at 1995 or 96. Of course, the interesting thing is that you can't ask the monkey in a straightforward way, when are you aware of the decision? So that's a nice wrinkle that you have with human experiments, you don't have in the monkey experiments. On the other hand, the monkey experiments tell you something about localization in the brain, so that you could, focus in on parietal electrodes or particular frontal electrodes and see, like you did in your other experiment, does that do as well or possibly even better than looking across all 128 electrodes?
Yes, so I mean, that's exactly what we plan to do here as well, because the previous studies, like I mentioned, Libet and all these, they look at readiness potential, and your readiness potential is, it's in the motor cortex. It's sort of, you prepare to move, but sort of logically you will think, before you prepare to move, there should be a signal, if it's a conscious decision, sort of from the frontal lobes, the higher order decision-making center, to the motor cortex to say, prepare to move. So we want to do something similar, of course, to see if we localize certain or use just certain electrodes, what does that do to our accuracy? And then so hopefully we can also then try and, in a way, localize where the decision originates from. So there's still a lot of fun work one can do with all the data.
Okay.
Then quickly, the last one I want to mention is, again, people can argue and say that, again, a urge to press a button left or right, there's no real world significance. So it's not really a free will choice in the sense of the ones we make every day that actually has consequences. So we are trying to address that one as well. So this is quite a fun project we started recently. So in this one, we got 24 participants, and they were blind to the actual purpose of the study. So we just told them that, listen, we're looking at a way to choose jury members for a trial. So you have in EEG, we want to see what happens with the brain signals in your decision making in sort of a trial situation. So we had 24 participants. We divided them up into 2 groups, and we gave them cases like this. So usually with this stuff, you have like a fixation cross, a person looks there, and then you get your question, their fingers again on the keyboard, and it will be a question: who would you convict? A man accused of attempted rape or a woman accused of murder in self-defense? I have to add, before the time, we gave them sort of a longer summary of each of the cases. This is just sort of the highlights so that they can remember the case. They had a whole bunch of cases to work through, and then we show them this, and they just press, left or right, who would they convict? So that's one half of the group. And the other half looks exactly the same, but you'll see this half we asked, who would you acquit? Same question, who would you convict, who would you acquit? 24 participants, 360 questions per participant, so sort of 360 data points per participant. But this was also further divided up into deliberate questions and arbitrary sort of decisions. So for half of the cases, we said, listen, we're not using this data, just arbitrarily press left or right. That doesn't matter. And this was just to see if, do we get the same signals for an arbitrary choice, like the deliberate choice where you just left or right doesn't really matter, versus a deliberate, something that really matters. And just to check our results, so this is just to show that you're on the left. So this is the two groups, the acquit group and convict group, and the response time for deliberate choices versus the arbitrary choices. And so they spend a bit more time. So it looks like they are sort of more invested in the deliberate choices. And you can see that here as well. So of course, with things like this, there's no right answer, but in a way there are less wrong answers, right? So on this side, so you can see it's sort of kind of random whether they press left or right for convicts and acquit groups, but for the arbitrary blocks. For the deliberate blocks, you would expect it to be sort of a mirror image because of the way we set it up. So for the acquit group, we'd expect when they press left, the convict group would press right, and for convict, when they press left, you would expect the acquit group to press right. Okay, and that's sort of what we see here. So just to show that the people probably did approach the deliberate choices differently than the arbitrary choices. And then just quickly, lastly, and with this, again, we see the same sort of limit trend in the ERP. It sort of just swaps around, but that just depends on your negative axis. A lot of people put the negative at the top. So again, we see this, what they call the readiness potential, this build up at around 500 milliseconds before action. We see it for both the arbitrary and deliberate choices. So again, there's no real difference in how they approach their choices or their decisions. Of course, the next step is to use the machine learning. We haven't done that yet, but to use the machine learning algorithm and see if we can predict, again, a bit earlier, will they press left or right on, especially on the deliberate choices, and see, can we predict where the person will acquit or who he will acquit, who he will convict. And so this is a real, sort of a more real free will choice. We'll see if we get the same results. And I see that's about time, but luckily I'm also about done. So in a nutshell, that's a couple of the studies we're working on with using machine learning and EEG data and seeing how we can better understand the brain and what goes on. And yes, I thank you. If you want to ask me more detailed questions, I don't have all the technical answers now, but you can send me an email. It's pretty easy. It's just dawie@sun.ac.za. But yes, I'm open to questions. Thank you.
Thank you so much. That was really wonderful and very, very interesting. One of the saddest parts about Zoom is that we can't actually applaud for you. So, I've taken to using the little like clap symbols and
Thank you.
It's great that we get to, normally you wouldn't have gotten to come to Alabama and given this kind of presentation, but so I'm glad this was an opportunity through virtual.
Thank you.
Thanks again, Dawie. Thanks, Alan, for asking some questions throughout. If anyone else has questions, please feel free to put them in the chat and I'm happy to read them out, or our visiting faculty, we've got several members, you guys can unmute yourselves and ask questions.
So just on an interesting note here, I visited Alabama last year, October. I was there visiting Danielle, for the day.
Very nice. That was,
Yeah.
We have nice weather here in the fall, so you'll enjoy that in Mississippi too. We have a question from one of our PhD students. How do you overcome the problem of data leakage during training in a single participant where you achieve 99% accuracy?
I'm not exactly sure what they mean with data leakage.
I can. BJ, do you want to unmute yourself and ask or clarify your data leakage question?
Hello, doctor.
Yes. Hello.
Yeah, so data leakage in the sense, if we use the same information in training, and if you there are some correlated information in the testing, then your training model has already known the information about the test data. So that is called the data leakage.
Okay, but that's exactly why we from the start split the data. So once we collected the data, we take 75% of the data and we only use that for training. So do all the training, build the models and that. And the other 25% we sort of put in the vault somewhere until we have our model, and then only then do we test.
But that 25% of the data also contains from the same subject, right? We don't have inter-subject variance in your training model.
Well, from what I've talked about now, in 3 of the cases, you're correct, but there was the one where we only trained on so with a semantic categorization. We had the 4 participants. We train on 3 of the 4. So the one guy is completely unseen data. So we only train on 3 of the 4, and then we try to classify on the 4th person, and we got really, really bad results. So we are looking at things like that as well. I didn't present all the data, but even with the sort of the limits, just the left, right button presses, we also looked at if we only train on one participant and then classifying his data versus if you train on all of them. In that one, we didn't sort of train on 20 of them and try to classify the 21st guy. But of course, that's stuff you can play around with.
Yeah, so that's why I was suspecting that the maximum, around 10% accuracy might be the case of data leakage, because the training model has already known the information about the test data from a single subject. If we have a cross, like leave one subject out validation, then we might overcome the problem of data leakage. Like, yes, but as you said.
I don't think, so I don't think data leakage is that big a problem here, because, I mean, it sort of depends on the question you're asking. In this case, in some of the cases, we're not really interested in whether it's generalizable across people. It's also interesting just to know if you train on a person, can you also classify him? So you answer the question of, is there a specific way his brain encodes the information? And is that way the brain encodes information, is that sort of accessible to us? And training on one person and classifying on that same person, you sort of answer that question, whether it's even possible to sort of decode how the brain encodes information.
Okay, thank you for your information. Thank you.
You're welcome.
Do we have any other questions from any of our seminar visitors today? I actually have one that's kind of speculative. So I'm colorblind, and when you were describing one of your initial tests where you show different presentations of red and purple, I was just wondering how something like a color deficiency is going to affect some of your readings.
Yeah, that probably will affect it. It's a good question. I hope the students were prudent enough to actually ask the participants whether they are colorblind or not. That would definitely affect it. I mean, that's also interesting. And yeah, that's an interesting question. I'm not too familiar with exactly the sort of physiology of color blindness. I know that it can be that there's a certain rod or cone or something that you don't have. But I'm wondering now, while you're asking this question, is there also a form of color blindness that sits more where the problem is more localized to the brain? So the eye has all the necessary equipment, but the problem is in how the brain processes the data. And then it becomes interesting whether you can still maybe classify using the EEG data whether the person saw a difference between colors, even though he's not consciously aware of seeing the difference between the colors.
I can answer that question.
Oh.
And that the most common kinds of color blindness are associated with deficiencies in the cones. In particular, red and green cones, where either one is missing or they're so similar in their chromatic absorption curve that you effectively only have a reddish green cone and a blue cone. So, and there are other, retinal variants that are of color deficiencies that are less common, but there also is cortical color blindness called achromatopsia that is mostly associated with some sort of lesion, a stroke, and a part of the visual cortex that's specifically associated with color processing. So that exists as well, and that can manifest, for example, in a loss of color constancy, which is to say the inability to recognize a color as a particular color independent of the light source that's on the scene, which is this kind of, very cool perceptual constancy that we normally have. So that's a brief statement about it.
That's interesting. There's also a phenomenon called color. No, I forgot the name. Blind sight. There we go.
Yeah.
And that's sort of also a cortical blindness. So the participants or patients, I don't know what to call them, according to them, subjectively they are blind. They can't see, but people will show them a shape and ask them, what shape do you see? And they say, I can't see nothing. And they say, take a guess. And they're guessing well above chance. And so the information is coming in. It's just there's different pathways in the brain. So something is happening. The brain is processing some of the information, and it's sort of there somewhere in their subconscious. They actually have the answer.
Yeah. It's usually thought that what's happening there is that, for example, primary visual cortex was damaged or wiped out or whatever, and yet those other pathways via other thalamic nuclei are intact. And so you're not, as you say, you're not consciously aware of what's going on, but there is some kind of processing that you can do.
Yes.
Even though you have no confidence about being able to point where the thing is or what it is.
Yeah. It's really interesting and fun stuff. Love it.
Yeah.
Thank you both. I learned something new about my own color blindness. Thank you. We have one more question in the chat, and the student wants to know if you saw a difference in data between male and female participants.
No, but honestly, I don't think we really checked for that. We didn't try to see if there's a difference. So we didn't really control for that. The only thing we control for that's known to sort of affect the data, especially with let's say this left-right button presses, is your handedness. So we made sure we only had right-handed people in the studies. Yeah.
All right. And then one more question. And then I know we're a little over, and I appreciate everyone sticking around because this has been a very interesting conversation. Are there differing values in different age groups, or did you look at different age groups in the participants?
Again, unfortunately not. Like 99% of EEG studies, and that's sort of a big problem across the world in the studies. We're working with what's called the weird population. It's Western, educated, industrialized, rich, democratic. I mean, basically you use students. So the age group is 18 to 22 mostly. So it's sort of a very small specific group. So didn't really look at age differences. We just forced the students to participate in the studies. So it's
Well, thank you very much again, Dawie. Students, you can log off now. Thank you for sticking around through the end of class. The speaker and I and Carrie will stay on for a few minutes to make sure we've tied up all of our official business. And I will see all of you next week at 1:25. I will be sending more information about that probably Monday. Have a good weekend, everyone.